Welcome to the Orbital Transports Podcast, your go-to source for everything happening in the world of small satellite missions and space logistics. Every week, we dive into the latest innovations, mission strategies, and the technologies shaping the small sat industry. We're thrilled to have you on this journey with us as we explore the frontier of space together. Let's get started.
Hey everyone, and welcome back for another deep dive. Today we're taking you behind the scenes of something truly fascinating.
Okay.
Antennas for small satellite missions.
Yeah.
Now you might be thinking, antennas?
Yeah.
Those things on my roof.
Right.
But trust me, these are not your average TV rabbit ears.
That's right. We're talking about antennas that have to survive the harsh environment of space,
Wow.
transmit data over incredible distances,
Yeah.
and do it all from a satellite that might be smaller than a microwave.
We've got some excerpts from a technical article here.
Okay.
And our mission is to break down how engineers choose the perfect antenna for each satellite's job.
Right.
Think of it like this.
Okay.
You wouldn't use a bicycle to deliver a grand piano, would you?
Exactly.
Yeah.
Each mission has very specific requirements.
Yeah.
Let's imagine two different missions.
Okay.
One is a constellation of satellites in low Earth orbit,
Okay.
providing super fast internet.
Gotcha.
And the other is a deep space probe heading out to Jupiter.
Those need completely different antenna setups.
So where do we even begin?
Yeah.
What are those key factors engineers consider when they're choosing an antenna?
So the first thing they look at is the type of orbit.
Okay.
It makes a huge difference whether your satellite is whizzing around a few hundred miles above Earth
Uh-huh.
or parked way out in geostationary orbit,
Okay.
tens of thousands of miles away.
So closer to Earth.
Exactly.
Less shouting required.
Yeah,
But what about those satellites way out in the cosmic boonies?
exactly. The further out you go, the more powerful your signal needs to be.
Yeah.
And that's just one piece of the puzzle.
Oh.
They also need to think about data rates.
Okay.
Think of it like this.
Yeah.
Sending a text message takes way less bandwidth than streaming a 4K movie.
That's a great analogy.
Yeah.
So a satellite beaming back high-res images of a hurricane
Yeah,
needs a seriously powerful antenna. Right?
absolutely. And then there's the frequency band.
Okay.
You wouldn't use a walkie-talkie to send high-definition video from Mars.
Right.
That's why
Hmm.
choosing the right frequency band is critical.
Uh-huh.
Deep space missions often use the Ka band because it can handle those massive data streams.
Now, this is where it gets really interesting.
Okay.
The types of antennas themselves.
Yeah.
It's not just about size, it's about how each antenna sends and receives signals.
Right.
Our article starts with omnidirectional antennas,
Okay.
which, as the name suggests, sends signals out in all directions.
They're like the beacons of the satellite world.
Okay.
Great for constant contact, especially in low Earth orbit where your satellite is moving fast.
Right.
And you need to maintain communication with ground stations as it zips around.
So it's like having a reliable cell phone connection.
Exactly.
Even if you're speeding down the highway.
Exactly.
But there's a trade-off.
Yeah.
Omnidirectional antennas are great for coverage,
Right.
but they're not the best for sending large amounts of data quickly because their signal is spread out.
Right.
It's like trying to water your entire garden with a sprinkler instead of a focused hose.
Yeah. That's a good analogy.
So for those data-intensive missions,
Right.
we need something a little more targeted.
You got it.
Okay.
That's where directional antennas come in.
All right.
They focus their signal into a narrow beam, kind of like a laser pointer.
Okay.
This makes them ideal for long-range communication,
Yeah.
especially when you need to send a lot of data.
Okay, so these are the workhorses for deep space missions.
Exactly.
Those signals traveling millions of miles, it's mind-blowing how we can focus them so precisely.
It really is remarkable.
Yeah.
And directional antennas don't have to be huge satellite dishes either.
Oh, okay.
Some are surprisingly compact,
Yeah.
designed to fit on smaller satellites.
Now, we've talked about our all-around communicators and our long-range specialists, but
Mhm.
what about those tiny CubeSats, the ones that are barely bigger than a loaf of bread?
Right.
How do they manage to send and receive signals?
That's where patch antennas shine. They're incredibly compact and can be easily integrated onto the surface of a small satellite. It's like having a built-in antenna on your phone,
Right.
except it's sending signals to Earth from space.
So they're perfect for those missions where size and weight are at a premium.
Exactly.
It's amazing how much technology we can pack into these tiny satellites.
It is. And then we have the showstoppers of the antenna world,
Okay.
phased array antennas.
Wow.
These are the most sophisticated type,
Okay.
allowing the satellite to electronically steer its beam without any moving parts.
Right.
Imagine being able to sweep your antenna's focus across a wide area,
Oh, wow.
tracking targets or adjusting coverage on the fly.
We've seen how fixed antennas work,
Right?
but what if you need an antenna that can change its focus on the fly?
Exactly.
That's where phased arrays come in.
They're incredibly versatile
Yeah.
and becoming increasingly important for applications like Earth observation,
Uh-huh.
where you might need to track a moving storm or monitor a specific region.
All right, so you've got a good handle on the different types of antennas out there.
Okay.
But how do engineers actually know which one is going to perform best for a specific mission?
Right.
It's not like they can just launch it up and hope for the best.
No, you're absolutely right. Before any of these antennas go anywhere near a launch pad, they have to prove themselves.
Oh, really?
We're talking rigorous testing
Uh-huh.
to make sure they can handle the wild ride of space.
Okay, pop quiz time.
Okay.
What separates a stellar space antenna from a cosmic dud? Let's dive into those performance metrics.
One of the key factors is gain.
Okay.
Basically, how much the antenna can amplify the signal in a particular direction.
Right.
Imagine you're shining a flashlight.
Okay.
A narrow beam will be brighter than a wide one because you're concentrating the light.
So a high-gain antenna is like focusing that flashlight beam across millions of miles.
Exactly.
That's incredible.
And a high-gain antenna is crucial for those deep space missions where every bit of signal strength counts. But there's a trade-off.
Oh,
The narrower your beam, the more precise you need to be with your pointing.
okay.
Think of it like aiming that laser pointer.
Uh-huh.
A slight wobble, and you miss your target completely.
I'm starting to see how complex this gets.
Yeah.
It's high gain for long range.
Right.
Well, what other metrics matter?
Another one is fractional bandwidth, or FBW.
Okay.
It basically tells us the range of frequencies over which the antenna can operate effectively.
Okay.
A higher FBW means more versatility.
So it's like having a universal adapter that works in different countries instead of needing a specific one for each.
That's a great way to put it.
Yeah.
Think about a satellite that needs to send different types of data back to Earth.
Uh-huh.
Maybe high-resolution images,
Hmm.
telemetry data, and even scientific measurements.
Right.
A high FBW allows the antenna to handle all those different frequencies simultaneously.
Okay, so we've got gain FBW. Anything else on our antenna report card?
Oh, absolutely.
Oh.
There's the radiation pattern, which describes how the antenna's energy is distributed in space.
Right.
Think of it like a footprint.
Okay.
Some antennas have a wide footprint covering a large area,
Gotcha.
while others are more focused like a spotlight.
So it's all about making sure the signal reaches its intended audience,
Precisely.
whether it's a ground station on Earth or another spacecraft?
Then there's polarization.
Okay.
You know how polarized sunglasses reduce glare by blocking certain light waves?
Yeah, they're a lifesaver on a sunny day.
Well, antennas need proper polarization too.
Hmm.
It ensures that the signal is aligned correctly for reception at the other end.
Okay.
Otherwise, you're basically trying to fit a square peg in a round hole.
So much thought goes into making sure these signals get where they need to go.
Yeah.
But let's not forget, these antennas are operating in a pretty extreme environment.
Right. We can't just send them up there without making sure they can handle the rigors of space.
Yeah.
Imagine packing for that trip. You'd need a parka and a swimsuit for your antenna.
Because space weather is no joke.
It is.
What kinds of challenges are we talking about?
Well, for starters, those extreme temperature swings.
Okay.
1 minute your antenna is baking in the scorching heat of direct sunlight.
Uh-huh.
The next, it's plunged into the frigid darkness of Earth's shadow.
Talk about a cosmic roller coaster.
It's brutal.
Right.
And those antennas need to be made of materials that can handle these wild temperature fluctuations
Right.
without warping or cracking.
Yeah.
Thermal stability is key.
But it's not just the temperature, right?
All right, yeah.
There's also that constant bombardment of radiation.
Absolutely. Cosmic rays and solar flares are like tiny bullets whizzing through space.
Wow.
And they can wreak havoc on sensitive electronics.
Right.
So those antennas need to be radiation hardened
Okay.
to withstand that constant barrage.
It's like giving them a suit of cosmic armor.
It is.
And then there's the threat of space debris.
Oh, yeah. All those bits and pieces of old satellites and rockets
Yeah.
zipping around at thousands of miles per hour.
Ugh.
Even a tiny fleck of paint can cause serious damage if it hits at the right, or should I say wrong, angle.
So it's a delicate balance.
It is.
The antennas need to be lightweight for launch,
Right.
but also incredibly tough to survive those potential impacts.
Exactly. And that's why testing is so crucial.
With all these threats in space, it's crucial to rigorously test these antennas before launch.
They really do simulate every possible scenario.
Wow.
They bake them, freeze them, shake them violently to mimic the forces of launch,
Wow.
and even blast them with radiation.
So they really put them through their paces.
They do. They want to make absolutely sure these antennas can handle anything space throws at them.
It sounds like these tests would make even a seasoned astronaut a little queasy.
Probably.
So what's one of the key tests they put these antennas through?
One of the most important is thermal vacuum testing.
Okay.
They basically create a mini space environment right here on Earth,
Oh, wow.
sucking out all the air and cycling the antenna through those extreme temperatures.
Wow.
They want to make sure it doesn't crack, warp, or malfunction under those conditions.
So it's like giving the antenna a taste of space before it actually goes there.
Exactly. Then there's vibration testing.
Okay.
They shake the antenna violently to make sure it can withstand the intense vibrations of launch.
Oh, gosh.
No loose screws or rattling parts allowed.
I can only imagine what that sounds like. And of course, they have to test for radiation, too.
Oh, yeah. They expose the antenna to high levels of radiation, simulating the harsh conditions it'll face out there in the cosmos.
Yeah.
This ensures that the electronics won't get fried by those pesky cosmic rays or solar flares.
Wow. It's incredible to think about all the work that goes into designing and testing these antennas.
It is.
Okay, we've learned a lot about how antennas are designed, tested, and how they actually work in space.
Right.
But what does this all mean for us down here on Earth?
Mm.
Why should we care about these tiny antennas on these seemingly distant satellites?
That's a great question.
Yeah.
And the answer is these small satellite missions are becoming increasingly important
Oh, okay.
for a whole range of things that impact our daily lives.
So it's not just about sending probes to distant planets?
Not at all. Think about weather forecasting.
Okay.
Those stunning images of hurricanes and storms
Yeah.
come from satellites equipped with powerful antennas.
So those antennas are helping us track those storms and keep people safe.
Exactly. And it's not just weather.
Oh,
Small satellites are being used for everything,
okay.
from monitoring climate change to providing internet access to remote areas.
Wow.
And the data they collect is only as good as the antennas that transmit it back to Earth.
So those antennas are kind of like the unsung heroes of space exploration, enabling these small but mighty missions to make a real difference in our lives.
I like that unsung heroes,
Yeah.
because without them, those satellites would just be silent floating boxes in space.
And as we launch more and more satellites, the role of these antennas is only going to become more critical.
That's exactly right. And it brings up some interesting challenges for the future.
What do you mean?
Well, as space becomes more crowded,
Right.
there's a greater potential for interference between all those signals zipping around.
Mm-hmm.
Imagine a highway with thousands of cars all trying to use their radios at the same time.
It would be chaos.
It would.
So how do we prevent those antennas from drowning each other out?
That's where things get really exciting.
Okay.
Engineers are working on some incredible new technologies to make antennas smarter and more adaptable,
Uh-huh.
capable of filtering out unwanted signals and focusing their beams with even greater precision.
So it's like giving each satellite its own noise-canceling headphones, allowing it to focus on its own conversation amidst all that cosmic chatter.
It's an incredible challenge,
Yeah?
but one that engineers are meeting head-on. And as we push the boundaries of space exploration, sending missions further and further into the solar system.
We'll need antennas that can handle those incredible distances.
Exactly. Think about a mission to Mars. Those signals have to travel millions of miles, and every watt of power is precious.
So we need antennas that are not only powerful, but also incredibly efficient.
It's a constant drive for innovation, pushing the boundaries of what's possible.
Right.
We're talking about new materials, innovative designs, and maybe even entirely new ways of thinking about how antennas work.
This is blowing my mind. What are some of the things they're exploring for the future?
Well, some researchers are even looking at using lasers for communication in space.
Lasers like something out of Star Wars.
It sounds like science fiction, but it's becoming a reality.
Wow.
Lasers offer incredibly high data rates and super-focused beams, which means less interference and more efficient communication over vast distances.
It's incredible to think that we might be beaming information back and forth across the solar system using lasers.
It really is an incredible time.
What a time to be alive.
The future of space communication is full of incredible possibilities. But even with all these advancements, the fundamental principles remain the same.
You mean those key factors we talked about?
Yes.
Orbit data rates, frequency bands, then those different types of antennas?
Exactly. Those are the building blocks. And understanding them helps us appreciate just how complex and ingenious these systems really are.
We started this deep dive with what seemed like a simple question.
Yeah.
How do you choose an antenna for a small satellite mission?
Right.
And it turns out it's anything but simple.
You're right. It's a whole world of engineering challenges, from figuring out how to focus those signals across vast distances
Right.
to making sure those antennas can survive the brutal conditions of space.
We talked about those extreme temperature swings, the constant radiation bombardment, and even the threat of impacts from space debris.
Right.
It's amazing that we can build something so delicate, yet so resilient.
It's a true testament to human ingenuity and our relentless pursuit of exploration.
And as you said, it's only going to get more challenging
Yeah.
as space becomes more crowded and our missions become even more ambitious.
It's a constant evolution.
Right.
We're always pushing the boundaries of what's possible, finding new ways to make these antennas smaller, more efficient, and more capable.
So what's the one thing you want our listeners to take away from this deep dive into the world of small satellite antennas?
I think it's the realization that these antennas, often hidden from view, are the unsung heroes of space exploration.
Oh,
They're the vital link that connects us to those distant missions, enabling them to send back the data that expands our understanding of the universe and our place within it.
beautifully said. And for our listeners who want to explore even further, I encourage you to look up images of different antenna types.
Yeah.
You'll be amazed by the variety and ingenuity of those designs.
From the elegant simplicity of a dipole antenna to the mind-boggling complexity of a phased array, each one tells a story of engineering brilliance pushing the limits of what's possible.
So the next time you see a stunning image from space, take a moment to appreciate the antenna that made it all possible.
Yeah.
Thanks for joining us on this episode of the Orbital Transports Podcast. If you'd like to learn more, reach out to us on LinkedIn or visit our website at orbitaltransports.com. We'd love to hear from you and help you navigate the next steps of your space mission journey. Until the next time, it's onwards and upwards.